Welcome to this short screencast on injection moulding processing temperatures. And there's only one learning outcome from this presentation, and that is to understand why correct processing temperatures are critical for injection moulding. So, first thing we're going to do, we're going to have a look at the melting curves for a low density and a high density polyethylene. These curves were generated through DSC, or differential scanning calorimetry. And what they show is they show a distinct melting point for both the low density polyethylene and the high density polyethylene. And when you look at the graphs, we can see that there's a peak there for low density polyethylene at 109 degrees C and for high density polyethylene at 132.5 degrees C. So now, we could probably postulate from this that for low density polyethylene with a TM or a melting point at 109 degrees C, that if we processed it or injection molded it at 10 to 20 degrees above this point, that should make sense. So let's go and have a look at a low density polyethylene datasheet and see is this correct. So the only piece of information I'm really looking at from this datasheet is the melt index, right? So that's going to give us an indication of what the MFI or the melt flow index is for this particular material, but more importantly, at what temperature and at what conditions this actual test was carried out. So when we go down and look at the melt index for this low density polyethylene, which is supplied by Dow Corning, the MFI is 0.75 grams per 10 minutes, and this test was carried out at 190 degrees C using a weight of 2.16 kilograms. So this 190 degrees C is 70 degrees or greater than 70 degrees above the actual melting point of the low density polyethylene. So let's continue. Now let's look specifically at the injection moulding processing parameters for a low density polyethylene. In this time it's supplied by Linal Basel, which are a well-known supplier of low-density polyethylene grades of resin. So when we look at specifically here at the Bartle temperatures, we can see that they're ranging from 204 degrees up to 232 degrees, with the recommended temperature of 221 degrees to 246 degrees. Now this is approximately 120 degrees above the actual melt temperature that was calculated during DSC. So why is there such a large difference between the melting point and the recommended processing conditions? And the reason for this large difference is that polymers are pseudoplastic. Therefore, as the temperature increases, or the processing temperature increases, their viscosity decreases. And that's what we're seeing here in this curve. So at the lower temperature, we've got the higher viscosity, and as the temperature increases, the viscosity decreases. On this second graph, we can see that as the shear rate increases, the viscosity also decreases. Now we'll have a look at this in further detail during the next screencast session. But for the moment, we just want to see why do we want such a high processing temperature in order to achieve a low viscosity? And the reason is that injection moulding is often involved in very complex parts, as we can see there on the left hand side of the screen. And unless we have a very, very low viscosity material, the parts won't be perfectly formed, and we'll get what's called short shots, and an image of which is indicated there on the right of the screen. Also, fast cycle times require that the material is injected into the mold at high rates. That means that we need low viscosity materials in order to get it injected into the mold very quickly. And the machine may become pressure limiting with high viscosity materials. So what does this mean? Well, this means that if we're using too high viscosity materials, we won't have enough pressure available to injection mold the materials into the mold. Now finally, what we're going to do is we're going to have a look at one of these very fast cycling processes in the next short video.
Here we can see the Airburg 720 manufacturing the 72 bottle caps in less than 3 seconds. I speeded up the clip so that you can have an overall view of the process and to get a feel for why we need the very low viscosity materials in order to achieve these very, very fast cycle times. In the last couple of seconds of the clip, we brought the video speed down to its actual value, and here we can see that the 72 parts are made in less than 3 seconds. Thank you for watching, and talk to you soon.